Hey everybody. So why are we having this discussion here today? Well, recently RISC Zero and Veridise collaborated to formally verify um, a proof of determinism for their Keccak circuit. And so this was kind of a big achievement for both of our parties. And the two of us here are the ones who basically did the brunt of the work on both sides. And we'd like to talk about, what went into this whole project, how it kind of happened, what it was like doing this project and how, what this means for verification um, more broadly. So maybe we can start by introducing ourselves. So Jacob, why don't you go ahead and get started and then.
Yeah. So I've been working at RISC Zero for a little over 2 years now. I was brought in as a compiler engineer and sort of a programming language designer of sorts for our zero knowledge circuit domain specific language. I was very excited about this work. I'd been interested in programming language theory for a long time and got into compilers because of it. But I didn't actually think anyone would ever, pay me to invent one, right? That seemed like a thing professors do, and I'm no professor. But sure enough, they wanted that. So I've worked on a bunch of different projects. The big one has been that domain-specific language, Zergen, as well as sort of a lot of tooling, ecosystem, performance sorts of things all over the place. It's been very interesting. What about yourself? What is it that you do at Veridise?
Yeah, so at Veridise, I do multiple things. I'm the head of ZK tooling, so I'm in charge of all the ZK tooling related stuff that we build. That includes the tool that we use to prove determinism, Picus, and I'm also I've done a lot of work as an auditor for looking at ZK circuits, finding bugs in them. So yeah, I mean, I think both of those, I think were a good fit for working on this project. Yeah.
Yeah, absolutely. We've worked together, I guess, in both capacities, both with you as an auditor and
Yeah.
as an engineer on tooling. But maybe you could tell us a little bit more about what Picus is and what it does.
Yeah, so Picus checks an important property called determinism of ZK circuits. So basically, what determinism means is that you have some circuit, it takes some inputs and produces some outputs, and determinism essentially says that this circuit encodes, a function. And this is really important because a huge class of bugs that we see out in the wild are called under-constrained bugs, so solutions to the circuits that the developer didn't intend. And so now if you can prove this property called determinism, then you know that these really nasty class of bugs are just not there. And so, yeah, we built Picus kind of to prove determinism, and it's actually really nice because it can find actual instances of both under-constrainedness because it can generate counterexamples, and it can actually formally verify that your circuit is deterministic. So, yeah, I mean, and we started with Picus a long time ago as a research prototype, and I think we've gone a long way to making it actually usable in a lot more production contexts, like on RISC Zero's circuits. So I'm excited to see kind of where we go from here.
Yeah, it's definitely some really impressive work. I think it's kind of funny that when we were first sort of engaging with Veridise to do an audit of our circuit, you showed up to one of those initial meetings with a couple of bugs already in hand. It was very convincing that both that Picus could very practically find real kinds of bugs in practice in a real large production ZK circuit, and the prospect of being able to prove that you found all of them that we don't have anymore after we fixed them all is also very exciting.
Oh yeah.
It was very persuasive as well, just to show up with them already in
Yeah,
hand.
yeah.
Why did you do that? How did you do that?
So I think I remember our head of auditing, Ben Sapansky, was like, it would be really great if we can actually audit the zkVM. They're like one of the bigger players out there. And, one thing that would be really impressive is if we can actually show that our tooling works on their stuff. So I spent a weekend kind of hacking an extractor together, to kind of extract some of the smaller circuits that are out there. And then it just turned out that there was an under constraint bug in one of them. So I was a little lucky, but kind of glad it worked out. So, well, maybe not glad.
Well, we don't try to put bugs in our code, but
Yeah.
certainly when we do find them, we try our best to make sure that we have found all of them, that there aren't more similar bugs lurking around. And so Picus was really, really a very good candidate for doing this, in that, in our experience with, previous audits and previous iterations of our circuits, this class of bugs of missing constraints from the system was sort of by far the most common thing.
Yeah.
We've been fortunate to catch most of them in pre-production stages, but it's one of those problems that kind of keeps me up at night. Of, do we have these issues still?
So maybe we can build on that. So RISC Zero just generally has been known for taking formal verification pretty seriously. Like, you had engagements in the past to try to verify functional correctness of different parts of your circuit. So, I mean, maybe you can talk about that culture, like why you guys care so much about formal verification, and why you cared about determinism more. Yeah.
Yeah, so I think there's a couple of good reasons for this. One is just that, we're a bunch of real computer scientists, and formal verification is cool. It's fun to think about. It's interesting. It's and it's sort of an especially interesting thing for people in security to be able to say, like, oh, our software really is secure, and we have a mathematical proof. We have it on solid mathematical foundations that that's true. The other thing that's, really important about that, though, is that really the security of our software is very top of mind because of what it does. In zk and cryptography and blockchains at large, it's really, really important that you get your security right, because if you write software that has these sort of fundamental security flaws in it, it doesn't matter how good the theoretical foundations of your software in theory is. Like, is this approach to zk secure on paper? We want to know that our implementations match the paper that says it's also secure, right?
Yeah.
And the reason that this is so important is because if we're going to go and use this in a blockchain context where people are going to go and secure billions of dollars potentially with this, I really don't want it to be my fault if that gets stolen.
Yeah.
I think really, though, we've done as a company a really good job of cultivating a culture of security. A lot of, conversations around cryptographic properties of our systems, what assumptions we make, being really cautious with code review, all of these things sort of permeate the organizational culture that, like, even just hanging around the office, you'll hear conversations about this, that, or the other obscure mathematical topic. I think another thing, is that this kind of goes all the way up to the top, in that our CEO, Jeremy Brussel, wrote one of the first Wi-Fi crackers. He found a critical core mathematical bug in the old Wi-Fi security scheme. And so this is really that's the sort of people that we have at RISC Zero, and they're the sort of people that take these things very seriously.
Oh, yeah. No, I mean, there's obviously some kind of opportunity cost with all this verification, and it can be, it can take a lot of time and effort. And so maybe we should start talking a little bit about that, and kind of what the pain points were, like what the effort what was the effort that was required, like what were the challenges that we both kind of experienced. So maybe we can start with you on this one, and then you can sort of talk about it from your side, and then I'll explain. I'll talk about it from my side.
Yeah. So just to be clear, you're sort of asking about, for the sake of integrating Picus, like, what was hard and where do we see maintenance burden going forward,
or more like, there's, in general, if you're doing some kind of verification task, it might take like 6 or 7 months of, like, a good engineer dedicated to this, and who knows where it'll turn out, right? Like, there's a risk associated with it. It's tough. And so I want to talk about, like, when it came to using Picus, was it one of those things where it felt like it was gonna take forever to get things done, or did you sort of see kind of the light at the end of the tunnel early on? Yeah, maybe you can.
Yeah, I think the light at the end of the tunnel was very clear early on. I think Picus offered a very practical and useful sort of path to value, in that, when I was first asked to sort of scope out like what was involved on our side to be able to use this tooling, I sort of looked at it and I said, oh, well, like of the things that I can foresee, it's probably, a week or two of work, and then there's sort of a long tail end of the unknown unknowns or the known unknowns, where, we'll just have to figure that out and see what it takes, right? But even, within a week, really, of sitting down to start using this tooling, we were able to start, proving that certain fragments of our circuits, of our real circuits, didn't have determinism bugs. It
Yeah.
was actually very, very quick.
Yeah.
In terms of getting to the full proof, it was only what, 2, 3 months
Yeah.
maybe.
Yeah. Hmm.
So as far as verification projects go, I think that's pretty fast. A
Yeah.
lot of large scale verification projects of like production software often takes a
Right.
year or
Right.
more.
Yeah. Yeah.
Obviously, this isn't a full formal verification, but to
Yeah. Yeah.
use this tooling and rule out this class of bugs was surprisingly fast. And the other thing that makes it very exciting is the fact that we can, that the verification is ongoing, that it's fully automated. And so as we continue to work on and evolve our circuits, we're able to continuously verify that we still don't have any of
Yeah.
these bugs.
Yeah.
So in that sense, you've actually made it very easy for us. What about
Yeah. Yeah.
on your side? What do you think?
I think a lot of the things that, so I think there were two kind of phases to this. One was we did the audit at first. This was a period of several months where I kind of extended that little hacky extractor that I wrote to get more circuits and use Picus to check their correctness. And I sort of noticed certain things where Picus was kind of struggling, which was as you kind of compose circuits together, things didn't scale very well, right? So to
Mm.
make that scale, we definitely made Picus a lot more of a modular tool, being able to reason about different parts of the top level circuit, and so independently. So that made things much more scalable. And then when it came time to actually do this, collaborative effort on checking your new Keccak accelerator,
Mm-hmm.
I think that the kind of changes we had to make were relatively minor after that. There were like, as anything happens, it's like, hey, Picus is not verifying this thing, what's going on?
Yeah.
And I take a look and it's like, okay, maybe we can make our range analysis a little better. Okay, we do that. Then it's like, okay, for some reason, I really expect the circuit to be proven deterministic. Like, what's going on? It's like, okay, maybe our static analysis can be improved and can better catch certain patterns. And then, we sort of go up and it's like, for some reason, when I use the CVC5 finite field solver, and then when I use this integer solver, it works on some stuff and not the other. It's like, okay, let's add multi-solver support. And so I think there were like a few little things here and there that we were able to add. And I think the main thing is that we were both like kind of passionate about getting this done. So we were able to get it. We were both able to find the issues in Picus really fast. And then I was able to kind of iterate on it fast. So I think that's what really made it kind of go over the finish line.
Yeah, it was definitely a lot of fun. There was a lot of energy, I think, on the shared Slack channel of a couple of long evenings, the occasional Saturday of
Yeah.
like, oh wait, it's Friday and we're about to get this done. Ah. And so, it was very fun to see the energy that, that you brought to the project, and to be able to iterate really quickly with you on those things was great. I was also very impressed, honestly, with the sort of correctness of the tool, in that in the entire process of iterating on things, it was always like, oh, this proof takes a little bit too long. Can you help us,
Yeah.
can you make this run a little faster? And never like, oh, there's a bug in your tool. There
Yeah.
was not a single one
Yeah.
that we found. So it was
Yeah.
it was a very pleasant experience, I think, both in that, sort of the interface that you'd set up was nice, and that it was very, easy to use, and you were very fun to work with personally.
Yeah. I think, yeah, definitely having partners that are as enthusiastic as you are about a certain thing is like just makes things so much smoother. So no, it was great. All right, so let's see. I think now that we have verified this precompile, let's talk about next steps. So what is it that we're actually? This is just a kind of small part of the larger thing we're both want to see, which is a full proof of determinism. Maybe we can talk about the roadmap here. So
Yeah, that's definitely true. You know, we've reached a really good milestone here, but obviously we're not done yet. There's more work to do always. It is yeah, it is a good accomplishment though, I think, to have, you know, done a full proof of determinism for the one precompile, right? But the broader vision really is that we will be able to have a proof of determinism for all of our circuits, and all of them will be rerun, reanalyzed, re-verified on an ongoing basis. You know, it's really amazing that Picus, you know, works so nicely in our CI. I think the whole proof of determinism for the Keccak circuit takes about 2.5 minutes.
Oh, nice.
If we get the same results on all of our other circuits too, well, that's going to be great. But really that is sort of the goal, right? Oftentimes people, engineering organizations will look at formal verification efforts as like, okay, we're ready to lock this down. We're not going to change this thing anymore. But I think the real value proposition of Picus for us is that we can rule out this class of bugs, and we can save a bunch of time and money on audits. Not that we're not going to do audits anymore, but you know, we can iterate much more quickly and have confidence that we're not introducing these sorts of security defects.
Oh yeah, I think as someone auditing your code, if I know that there's no under constraint bugs, then that does keep my mind at ease. Yeah, definitely.
I imagine it makes your job easier as an auditor too.
Oh, of course, yeah. No, definitely.
I guess I'm curious, as like from the perspective of doing an audit, if you are asked to go audit a zk circuit and you are already given a proof of determinism from your own tool, you know, how much time does that save you, and what difference does that make in how you approach the audit?
I think it saves a ton of time. I think a lot of time that I notice myself auditing a circuit, it's spent trying to find under constrained bugs. That's like the biggest class that are out there. I think, you know, I can't quantify it in terms of, you know, does the audit go from 1 week to a day? But
Sure.
basically it's more about, you know, the kind of things that I look for are going to be a bit more like logical, or maybe there's going to be some over constrained bugs or things like that might show up. But I think the broader security impact of those kind of bugs is a little bit less than under constrained, just in general. So overall, I think, you know, definitely gives me a higher assurance that when I finish an audit, that there's not something super critical that can be used to exploit this protocol. Yeah, I can at least turn my attention on the other aspects, because I mean, RISC Zero's kind of there's a lot going on, and there's a lot of different areas where security matters, and so we can turn our attention to those. Yeah.
Yeah. And I guess just on the topic of bug frequency, I saw some interesting data that came out maybe in the last month or so from zk Security, where they this team had gone and scraped a bunch of audit reports and security bug trackers and all sorts of data sources, any source they could get their hands on, looking for real bugs in zero-knowledge cryptography systems. And I believe they found something like close to 70% of all zk bugs were circuit bugs, and about 97% or 96% of circuit bugs were under constrained bugs. So like if you multiply those two numbers together and assume this data set is representative, right, that means about 2/3 of the bugs in the whole system are under constrained bugs, which we've now proven are not in our circuits in particular.
Yeah. I think that's a major win in general, and I think you know, I think one thing we haven't talked about is kind of there's like a lot more things that kind of made all of this possible, and I think part of it is on the compiler side, stuff that you worked on. In general, I think it could be, you know, we were able to exploit things like modularity partly because of the design of the language, and so maybe you can talk a little bit about, you are working on this on Zergen, this DSL, and like kind of maybe think about formal methods like that with the idea of formal methods in mind. Like, how did you sort of how can a DSL be kind of designed to be amenable to formal verification? Yeah.
Yeah, that's a really good question, and formal methods were actually very front of mind for me from day one. When actually even day -1, when I was still interviewing at the company, and I was talking with our founder about the possibility of doing formal methods on circuits. Right, I was already sort of starting to think about some of these ideas were already forming. So really, the big sorts of things that came into mind at the language design level was, how do we make a circuit modular? How do we build in composability such that if you want to understand the behavior of a circuit as a whole, it suffices to just look at small pieces and reason about how they fit together. And so composition was sort of a fundamental fundamental design goal of the language. Another piece of it, though, was also to have some notion of a denotational semantics in mind for the language from the outstart of like, here's what this component really is as a mathematical object. Let that be very well defined, right? And so the core abstraction in Zergen is called a component, and it captures all the different pieces of a circuit fragment, a small piece of the circuit, and puts them all into a single bundle that you can reason about very nicely as a developer. And so what we found is that this has been actually very helpful both from the perspective of implementing a circuit, like, oh, we want to make this change, or we want to create a new version of our circuit that works this way. And it's also made it possible to do sort of refactoring and incremental changes into a circuit where that was harder before. As a concrete example of this, one of the things that we struggled with in the predecessor of Zergen was adjusting layouts with circuit changes. So you sort of had to commit up front to what the fundamental witness in the circuit looked like ahead of time, and then as you went down, you had to figure out how you mapped and reused those things in different parts of the circuit to do things efficiently. And fundamentally, that problem is now solved by the compiler, right? And so you have this nice, clean, top-level semantics that lets you compose things freely without having to worry about and potentially get wrong all those messy details down the stack. It's also, however, made it very convenient to extract a Picus in that the modularity was exactly the modularity system that you developed to use.
Yeah.
And that the representation of constraints also mapped very nicely onto what you'd already come up with separately.
Right. I think like in order to make Picus more available to be used with other languages after the V1 version, I think we had to kind of make a format that was kind of easy to translate to. And I think that one of the things that I noticed when auditing the circuits that you guys wrote, I think they were kind of designed in a way where it was very easy to see implicit assumptions that they had. Like some circuits may have expected some of the arguments to be, range checked in a certain way, or maybe there's different types of assumptions that I think as somebody, when I was using Picus, it was very easy to kind of write, okay, I need to add this assumption here that what the circuit expects, and then then when Picus verifies the code, it'll make sure that the assumptions actually hold. And so I think how you kind of design one thing I've been thinking about a lot is like how you design your circuits can really affect how easily it is to actually be able to verify. If things maybe are overly optimized at the get-go, then maybe it's harder to actually check. Obviously, that isn't to say your circuits are not.
Yeah, certainly we employ a lot of tricks, but we hope that the tricks that the circuit writer has to use are sort of high-level things that are hard for a compiler to catch, as opposed to, sweating the small stuff. In particular, we really didn't want it to feel like writing assembly.
Yeah.
And so I think that is something we got approximately right. Obviously nothing's perfect, but I think it turned out pretty well. And I guess I'll also add, we do at least have a lot of those, low-level optimizations, but they happen inside the compiler like you would expect in a language like Rust, as opposed to,
Yeah.
needing to do all that by hand.
Yeah, yeah, exactly. So now that we have this proof of determinism, a big milestone for your formal verification efforts, what's next on the horizon? What other projects are you interested in doing as a company with formal verification, and what should we expect?
Yeah, so the first one is actually not a formal methods thing, but now that we have this, way to very efficiently audit our circuits for under constrained bugs, one of the things that I'm really excited about doing in the compiler is to, get a little more wild with optimization. We've got sort of this nice guarantee now that we can get at this certain point in our compilation pipeline that we're not introducing this class of bugs. It's a good security guarantee that perhaps lets us, optimize a little bit more freely and iterate more quickly on our circuits. So rather than, putting out a major revision every once in a while, we might be able to put in a lot more small optimizations and make some of these, basically version our circuit more often, because it sort of reduces that security auditing burden. It's something that we can do much more easily, much more quickly. In terms of formal methods, of course, the sort of next thing that's very interesting is to move towards more functional correctness, to start figuring out, do our circuits implement RISC-V like we think we do, or do they perhaps implement something slightly different, right? Did we, in addition to having all the constraints we need, do we have the right constraints, and are we doing the right computation? That's a much harder problem. It's a much longer term sort of vision, obviously, but I think that's really where we're headed. We value formal methods a lot as a company, and we want to put that into our work.
Yeah. Oh yeah, no, I remember we were also talking, and I think there's a number of different avenues of things that we also wanted to look into. Like, one of the things is that you had published a really nice blog post that I hope a lot of people read or will read. And I think in that we talk about, okay, with any formal methods work, there's always some assumptions that we make. Like, right, you do this encode translation into the Picus's internal language. There's, what if there's some issues with that? Okay, well then your verification result doesn't correspond to reality, right? Likewise, if there's a bug in Picus, right, maybe that means that the verification result puts it into question a little bit, right? So I think having, some stronger guarantees, I think there's things that we can do to get a little bit stronger guarantees down the road. I think one of the things we mentioned was kind of having a verified translation, like translation validation between doing some kind of, between the, the circuit that you're, the Zergen circuit and the Picus thing that we emit. And also I remember on the Picus side, being able to kind of emit a proof that could be checked in lean would be really interesting. And I think there's still a ways to go to get to that point, but I think that's an interesting direction. Like, kind of transparency for automated verification tools is really interesting.
Yeah, absolutely. I think, like you point out, within our work on Picus, obviously we've taken sort of this snapshot within the Zergen compiler pipeline of, like, here's our representation of the circuit constraints. There are some transformations that we do afterwards that are not especially complicated. It's relatively innocuous things like inlining and common sub-expression elimination, but it's possible that there are bugs in those passes. And so one of these assumptions that you have to make in order to trust the verification result is that everything downstream in the compiler is correct. Obviously, I've gone to great lengths to get the compiler right, but software has bugs in it.
Yeah.
That's true. And so in the context of formal methods, right, these are called trusted code assumptions. When you verify code with a computer, you have to trust that the proof checking code of the computer is right, and that any transformations that you make after the fact preserve the property that you proved, right? And so, I'm very confident in our proof of the snapshot, And I also think it translates well into a proof of the whole circuit. But certainly we can do some better things to sort of, erase some asterisks, so to speak, here. And like you say, right, formally verifying the translation from the Zurgeon intermediate representation to Picus is a really would go a long way in that, to sort of make sure that we got that translation right.
And I definitely think it's doable.
Oh yeah.
Because I think the translation is relatively simple.
Mm-hmm.
I think there's a few things interesting details that we can talk about with like memory and making sure we encode that correctly. But for the most part, the translation is very simple, and I think it's definitely doable, and I'm kind of excited to see that.
Absolutely. Yeah, we actually might pretty soon start working on a formal semantics for our intermediate representation. So that would be a possible target for validating that translation. I guess I would also be curious to hear a bit more about what you have in mind for the future, your next steps on Veridice's side.
Yeah. Oh, there's a lot of things we're working on. I'm really excited. We've had a lot of discussions about, building an IR for circuit DSLs, and we have this grant from the Ethereum Foundation to build such an IR, and we call it LZK, meaning for a low-level zkIR, inspired by LLVM. And so, yeah, that's something we're actively building on, and we hope to build a lot of infrastructure so that the entire blockchain community can build, at least the ZK community can build a lot of security tooling that applies to not just one circuit DSL, but many. And I think that was one of the things we learned at Veridise, is that we have good tools, but at the time it was like very fragmented, working on some DSLs and not others. And we really want to make our tools applicable to a broad range of circuits. So yeah, I think that's kind of the main thing we're working on next. And I think we're also really looking to make Picus better. I think there's a lot of things I'm excited to try, and I'm hoping with this new engagement on verifying the full V2 circuit, I'm able to try these out, see what works, see what doesn't, and then iterate on that. So yeah, maybe we should end it there.
Yeah.
It's a great conversation, and hope we continue to see success on both our companies. So
yeah, thank you so much. It's been a pleasure.
yeah, see ya.